our next ADT is a set. So first, let's talk about what a set is. It's an unordered collection of elements. The elements can be added and removed, and you can also check whether or not an element exists, and that's basically the entire behavior of a set. It's analogous to the mathematical set that you learned about when you took CS 151, or the equivalent discrete math class. So a set is a collection of elements with no duplicates. It's often drawn in this way here on the right top corner because there is no order to the set, and so you can just see it as a big group, but there's like no associated order with the elements. Operations include, as I said before, just adding and removing from the set, and all of those operations are fast. In some implementations of sets, you can iterate or loop over the set. When you do that, they'll generally be in sorted order, but in some implementations, you can't really iterate or loop over the set. And I'll talk about why in a second. Oh, there's a typo. Just like all the other ADTs, the set also keeps track of its own size. So a big part about sets in compared to the other abstractions that we've talked about so far is that there's no duplicates. As you can see so far, the only abstraction that we've talked about that's able to keep track of order, at least a particular order, is the dynamic array. In C++, there's two different containers for sets. One is called set and one is called unordered set. Java, Python, and JavaScript also have sets, and set is generally the chosen word, and you'll also hear the term hash set, which we'll talk about why in a second. In C++, if you want to use the set, you would need to include the proper library at the top, and if you're using the regular set, you would use set, and then if you're using the unordered set, you'd have unordered set in here. Also, you can write your own. So there's two different implementations of the set ADT. We're going to talk about them a lot more throughout the class, and this is probably going to be most confusing slide in this slide deck. If this is new to you, which it should be, because that's why you're taking a class on data structures. But it's important that we talk about it up front, and then we'll keep revisiting it. So basically there's two ways to implement a set, and they're broken up into a regular set and a hash set. So in C++, this is the container called set, and then in C++, the hash set is called an unordered set, which is not my favorite choice of words. A regular set is very fast. The best part about sets is they have very, very fast lookup. So if you need to access something into a set, into a regular set, you can do that in log n time. We're going to talk more about big O. A lot of you have seen it in 141 or equivalent, but log n is pretty good. The way that the set is implemented is using something called a binary search tree. It is assumed that you don't know what a binary search tree is. We're going to learn about it in this class, but it's one of our data structures. It's just a tree that has special conditions, and so behind the set, the implementation is a tree, and trees are really fast. And the particular tree used is a binary search tree. A hash set, on the other hand, is really, really fast, so fast that it has constant time retrieval. So you can access something in a hash set in O1 time, which means it doesn't matter how many things are in your set using a hash set, it's always going to be constant time. That's able to happen through something called a hash table. Again, it's a whole topic that we cover in this class, and we'll spend a whole week or so on hash tables and what that data structure looks like. What I hope you get out of this is that sets are implemented in two ways, and they're both needed, so we like both of them. One is using trees, one is using hash tables. Trees are sorted, hash tables are not, and so they bring with them different pros and cons, and both are really fast. Pros and cons of the set. Again, there's no random access in a set. The only thing that we've seen that has random access so far is the dynamic arrays. All the rest of these abstractions don't have it, so if you need random access, they're not going to work. Sets do not have a particular order. So even the regular set, it does have sorted order, but it won't keep track of the order that you placed items in. It will keep it in sorted order, if that makes sense. So if you need to maintain an order other than sorted order, they're not going to work. They also do not allow duplicates as is. Because you're only keeping track of whether something is or is not contained, duplicates don't make any sense. But what is great about sets is they have very, very fast lookup. So anytime you are searching or looking up your data, sets are the way to go. However, a set can only tell you whether or not something does or does not exist, but can't give you additional information around the data. So a set is used if you just want to know if something has been visited, is contained, etc. The next abstraction that we look at will give us a little bit more information about the data, instead of just yes or no. Applications of sets. They're used a lot in databases. They can really help with understanding using things like unions and intersections that you learned about in discrete math, different combinations of things that are found in databases. Also just for simple things like is this or is this not contained? And we'll see a lot more applications for in databases for our next abstraction, which is maps. Like I've said in some of the other abstractions, they're also really useful in graph algorithms and generally in lots of algorithms. So let me just give you one example. So this is a graph, and again, it's assumed that you don't know much, maybe have never even heard of a graph, because that's what the class is going to teach you. But here is an example graph. You've probably used so many different things that act like a graph that it's easy to digest quickly. You could imagine that A and B are two different locations on a map, and the edge between it is the distance between those two locations. You could also imagine that it's any network, people, computers, or anything else where the nodes are the A, B, C, D, E, F, and the connections are how they're connected. So in graph algorithms, one of the things that's often useful is to know where you have visited. So if you're searching a graph, because there's so many different connections and so many different ways to get to different nodes, we often prefer to know what we have visited. That way we don't revisit nodes and get stuck in an infinite loop. So sets provide a really fast way for us to keep track of where we have gone so that we don't revisit. And that's it for sets. Thanks.